Okay, this is the last section of chapter 20 on sound. We're going to talk about interference, beats, and we're going to talk a little bit about FM and uh, AM, amplitude modulation and frequency modulation. Um, so we're going to talk about interference properties of all waves and wave motion, superposition of waves that may either reinforce or cancel each other. So here we see two waves that are in phase. So you can see this one adds to this one and you get double, so it reinforces. It's constructive interference, what we call constructive interference. But here you can see that these are out of phase. When this one goes up, this one goes down. And when you sum those two together, you get nothing. You get a straight line. So it's a destructive interference. And you get cancellation. So you can have constructive interference and destructive uh, interference. And I'll post a video on Canvas on where I did an experiment to where I moved a speaker one half wavelength, and you can see that the sound diminishes. You can also see it on a little screen on my the sound beam that I used in a couple of uh, lectures ago. So let's see, interference is a property of sound or a property of light or both A and B. Neither A and B. Well, it's a property of both light uh, and sound can uh, uh, can experience interference. Interestingly, the presence of interference tells a physicist whether something is wave-like. All types of waves uh, can interfere with one another, and there's a wave nature. There's a particle nature to light, but there's also a wave nature of light, and you can get interference. Okay. Two patterns of interference: constructive interference, the increased amplitude when the crest of one wave overlaps the crest of another wave. And there's destructive interference, reduced amplitude when the crest of one wave overlaps the trough of another wave. And that's what we see up in, we have the crest here, and the trough here, and the crest here, and they cancel. So that's what they're talking about here. Destructive interference, reduced amplitude when the crest of one wave overlaps the trough of another wave. Does this happen with transverse waves or longitudinal waves? Well, that happens with both. And they show you examples. The superposition of two identical transverse waves in phase produces a wave of increased amplitude. So this one starts going up, this one starts going up. They're in phase, so they reinforce one another here. Constructive interference. Here you can see the compression, rarefaction. Same here, compression, rarefaction, in the same timing. So you get increased intensity. Here this one's going up, this one's going down. So they cancel each other. This is destructive interference. Two identical transverse waves that are out of phase destroy each other when they are superimposed. So you get no signal. And two identical longitudinal waves, you have compression, rarefaction. Here it starts with rarefaction, compression, rarefaction, and compression, and you get nothing. There's no wave here. So the application of sound interference, the destructive sound interference in noisy devices such as jackhammers that are equipped with microphones to produce mirror image wave patterns fed to operators' earphones, canceling the jackhammer's sound. Now those around, people walking by, they'll hear it, but the operator wears special gear. This is how noise canceling headphones work. I'm wearing um, uh, AirPods, and I put it in noise cancellation, and it doesn't work perfectly, but it does diminish the sound. Um, so they are feeding, they're sensing the signal coming in, they reverse it, and you get noise cancellation. But the signal coming in from music or whatever, you still hear that. Application of sound interference, and I'm going to post a video where I do this. When I move one speaker a half wavelength, and you'll hear the sound greatly diminished. The sound interference in stereo speakers out of phase, sending a common binaural signal. If you have a binaural signal, the signal is identical. And if you just switch uh, the uh, the wires, you have a stereo speaker, but you have a binaural signal. If you just switch the wires, you're going to get cancellation out of phase. When one speaker produces a compression, the other sends a rarefaction, and vice versa. As the speakers are brought closer to each other, the sound is diminished as the compressions fill the rarefactions from the other speaker. And it's going to start at the low frequencies. It's going to start at the low frequencies, and as you closer together, bring them closer together, you'll only hear the high frequencies until you almost hear nothing at all. Now, beats. Change the subject, but I didn't want to start another part. Beats are periodic I should diminish this so that it doesn't interfere with the screen. Beats are periodic variations in the loudness of the combined sound from two sources emitting tones with small difference in frequency. Beating occurs due to the interference. The beat frequency is the difference of the frequencies of the individual tones. So we have one tuning fork. You can see that it's got a lower frequency. There's 1, 2, 3, 4, 5, 6. Six crests in this time period, and this one has 1, 2, 3, 4, 5, 6, 7, 8 crests in this one, and so you would hear the difference. Here you have constructive interference, and here you have destructive. This can happen. I don't know. I have experienced it where you pull up to a stop sign and your car's idling, and a car next to you is idling at almost the same RPM, but they're a little bit off, and you will hear a boom, boom, boom. You'll hear a beat that comes from the interference of the two engines. Listen out for it sometime. Um, let's see. Um, Applications: piano tuning by listening to the disappearance of beats from a tuning fork and a piano key. And then tuning instruments in an orchestra by listening for beats between instruments and the piano tone. You can tune a guitar by. Now I'm not a guitar player, so I don't know how it is, but I know you can if you press on the guitar string on a lower tone string, you can make it about the same as the string next to it, and you just tune them to where you don't hear beats anymore. Now they throw this in, uh, and I'm not really sure how it applies. This seems like this would be later on, but they do discuss it in the text, so I'm going to discuss it. Amplitude modulation. This is your sound signal, and this is your carrier signal, and you superimpose the sound signal onto the carrier signal, send it through the air. The receiver demodulates it and um, reproduces the sound that was transmitted. Oops, didn't mean to go that far. Now, frequency modulation. Here's the sound signal. Here's the carrier signal. But instead of varying the amplitude, you vary the frequency. You can see how when there's a crest, the waves are together. When there's a trough, the waves are spread out. So you modulate the frequency and transmit it, and then you demodulate it, and you get the signal back. I will have, I think I'm able to add a video where I do some modulation, and you can see visually the modulation. Um, so I'm not transmitting anything. I'm just in the lab playing with a couple of generators, signal generators. Um, that's what we scientists are. We just play with expensive toys. So okay, I think that's it for the chapter. And here we go.